Hello students, today we're going to be looking at what real analysis tries to fix. So imagine you are hired to build a massive beautiful brick house. You won't start by trying to sketch the roof high up in midair and then cross your fingers hoping the walls will float up to support it, right? If you try to build a home from the roof down, the entire project obviously will come crashing down around you instantly. You need a solid foundation before you can build upward. So, yet, for generations, this is exactly how humanity treats calculus and the advanced mathematics. The roof of our mathematical house is made up of the incredible, powerful tools, right? Derivatives, integrals, optimization formulas, and differential equations. These work wonders, and if you realize closely at what lies beneath them, you realize that they are resting on an unverified, shaky foundation in the perspective of early mathematicians, right? So let's trace the dependencies back towards why everything rests on the lowest level. To compute a derivative or find the area under a curve, you have to scope a concept called the limit. And what exactly is a limit, right? It's a way to describe what happens to a function as its inputs creep closer and closer to the target point, right? Without ever actually touching it. So that means to understand limits, you have to first break down an absolute unshakable definition of continuity and what it truly means for a line or a space to be smooth, connected, or completely broken. um if you dig even deeper and ask what does it mean for a line to be completely unbroken, right? You hit the ultimate bedrock question of what are numbers actually even made of. And if the real number line has any hidden microscopic gaps, or if our definition of a straight line is slightly fuzzy, then our limits will fall apart and continuity will fail and our calculus roof is collapsed. So real analysis was designed actually much later than calculus to fix this exact chain of structural dependencies. So this is where real analysis steps in to save the day, right? Its entire mission is to act as a rigorous construction crew for mathematicians and the branch of mathematics. So real analysis doesn't give you quick formulas to solve problems faster or memorize shortcuts for an exam, right? Instead, it goes all the way down to the smallest grain of sand or smallest piece of dirt and examines the fundamental properties of numbers and pours a flawless concrete foundation and proves every single step with absolute certainty. So we are going to be using ironclad logical certainty. And following Kenneth Ross's approach, we are going to rebuild this mathematical universe step by step from the ground up. We're going to be looking at whole numbers, uncovering why fractions aren't enough to fill a continuous line, and discover the hidden property, which is called completeness, that holds the real number line together. So let's just write that down for you to preview. You have completeness, right? Um, yeah, I guess that's kind of really what we're going to be looking at in these next couple of videos, right? So before we lay down our very first foundational stone, we're going to establish the rules of truth, and we're going to learn how to construct a logical argument that can never be broken, shaken, or doubted. So we have to transition away from the everyday guessing, right? Just uh, assumptions and observations. We have to transition from that into the formal mathematical rigor. So that's kind of what I guess discerns the standard empirical sciences and mathematics, right? Which is the fact that empirical science is built off of observations, looking at patterns and seeing if a hypothesis is true. Whereas mathematics is different. Observations do not lead to certainty. So in our next video, we're going to be looking at what mathematicians mean by proof. So thank you for tuning in, and I'll see you there. Thank you.